with respect to the x hat of k. Correct? You have to take derivative with respect to the x hat of k. Okay? So this is slightly easier, right? It's slightly easier because when I take the derivative of this guy, so substitute everything in, I only pick up one term. I only pick up one term, right? The terms where I have the x hat k. Okay? K minus 1 and k plus 1, they never come into the equation, right? So I only pick up one term, and then I assume that everything is continuous. I can switch the order between integral and derivative. Then I come up with something like this. Okay? Set it equal to 0 means that so you have you break this into two integral, right? Break this into two integral. One guy is like this, the other guy is like that, and your job is to find the x hat of k. Okay? So the solution turns out to be something like this. Now let's step back and take a look, see if it makes sense. What exactly is it trying to say here? The optimal reconstruction point, which is the red dot, should be where? Now let's take a look at the denominator, okay? So this is simply the integral of the PDF of x. So this gives us some number, right? It's just a scaling number. It's not that important, right? So this is a scaling number. This is just a scaling scalar. Okay. What about the guys up here? That's the expectation. That's the expectation of x. Okay. The expectation of x within the interval. Within the interval. With fx of x. So, if it's uniform, guess where the expectation comes in? In the midpoint. Okay? Fine. There's no problem. But if it's Gaussian, suppose I have a Gaussian like this, and this is the interval xk minus 1 and xk. Okay? The midpoint is here. Okay? That's not optimal. The optimal thing to do is the expectation, which will move this guy over a little bit. Okay? That's exactly what it's trying to say. Somebody already give you this xk minus 1 and xk. You cannot control it. Okay? But you can control the reconstruction. Okay? And in this case, what you should do is to move the reconstruction over to bias this region where it's more likely that x falls into play. Okay, and this will minimize the mean square error. Okay, so these are the two. So this is called the centroid rule. The centroid rule, which says that the optimal reconstruction point is the centroid of fx of x in this particular interval. If you move on to this interval, maybe it will happen to be in the middle. Okay, so it all depends. So those are the two fundamental theorems that we can say about quantizations. Now, but we run into a little problem, right? We're cheating. We're breaking up the problem into two parts, and then, okay, we solve the optimal encoder given the decoder, solve the optimal decoder given encoder, but we don't have any solution for the joint problem, right? Right? If the entire point is the point between x and x hat. Whatever happens in the middle, you don't really care. Okay? So that problem is being solved by Lloyd and Max all the way in the 1950s. Okay? Unfortunately, we need x hat k to solve for xk, and then we need xk to solve for x hat k. Okay? So it's a chicken and egg problem, right? Okay? And well, when you encounter a chicken and egg problem, the only thing you can do is think of something iterative, some kind of iterative algorithm. Okay, and so this is the idea is first being published by Lloyd in 1957, and then Max independently discovered the idea again in 1960, and they typically call the Lloyd-Max quantizer. So you're going to solve these two equations iteratively until D converge, or D doesn't decrease by a whole lot anymore. So this is an ad hoc engineering technique that allow us to run around the problem, because we just don't know what else that we can do. Okay? So basically, this is what happens. You have the nearest neighbor rule, and you have the centroid computation rule. Okay? And so you're gonna start here. You apply the nearest neighbor partitioning. Okay? And then you use the centroid computation on it, and then you update the code book. You feed this code book back here and try to do this again. And everywhere you go, you compute the distortion. Okay? And you let it run until D doesn't seem to decrease anymore. So in one of the homework assignments that we pass out today, we're going to have a simple exercise. You don't need to iterate. You only need to iterate maybe once. Okay? You're given a nice Laplacian. And then I ask you to design the optimal quantizer. And it turns out that with that problem set up, you don't you basically get the result doing this only once. Okay? So there are cases that you don't have to iterate anything. Yeah? But in practice, typically, we need to set up this problem. Okay? Now, the assumption is the PDF is known and stationary, and this is very important. Entropy has not been taken into account. Okay? So all the optimal things that we have been discussing about, okay, is just quantization by itself. Quantization by itself. We never take into account that we have entropy coder following up on our quantization solution. Okay? So that turns out to be a major problem. Okay? Because remember the goals for entropy coding is to generate as many similar symbols as possible. And in this case, hopefully 0, right? We like 0 a lot in compression, by the way. Okay, 0 means small, 0 means insignificant, 0 means you can throw them away. Okay? We only keep the large guys. We always throw away the small guys. So we like 0 a lot. Okay? The goal of doing quantizer is to generate as many 0 as possible. Okay? To generate as many 0 as possible, so that your entropy coder will do a very good job. Okay? So then, but I would like to discuss another type of quantization, which is actually being used in practice a lot. And this time, we actually take into account that we want to generate a lot of 0. Okay? So how do we do this? So this is the random variable x, and I assume that maybe it's living on the real line. Okay? Living on the real line means you need infinite amounts of bits to represent x. Okay? So that infinite amount of bits come in the integer form, decimal space, and all these binaries that describe the decimal part, the fractional part of it, right? Okay? So 1/2 means you have a 1 here. Okay? 1/4 means you have a 0 here and you have a 1 there, so on and so forth. Okay? The way that we represent binary using for fractions. Okay? So x is going to be a combination of integer part and fractional part in binary. So these are binary with assignments in the beginning. Okay? So x is here, y is here, and xs is there. Okay? And this is what embedded quantization does. I'm going to discard n integer bit planes. N integer bit planes meaning I discard n guys here and all the fractional bits. I'm going to throw away all the fractional bits. Okay? And further, I'm going to throw away several integer bits. The least significant bits. Okay? And I call this y. So this is going to be y. This is a very easy thing to do, right? This quantizer is very easy to implement. You don't need to do anything. In fact, x coming in, you throw away the guys in the back, and you only keep the most significant bits, the few most significant bits plus the sign bit. That's it. Okay, it's very easy to do in practice. It's absolutely wonderful. Okay, and it turns out that KPAC 2000 is using this embedded quantization technique. Okay, so let's investigate this and see how y behaves. Okay, how x hat behaves, so on and so forth. Agree? So let's see how y behaves. Okay, and you can think of this as the most significant information is being transmitted first, right? So first we're going to transmit the sign bit, then we're going to transmit the most significant bit, then we're going to transmit the next most significant bit, and we move on until we run out of bit rate. Okay? Which is a very, very easy thing to do in practice. Okay, so let's think about our mapping. Okay? What exactly is the mapping between x and y and the x hat? Okay? So x is the input of the quantizer, y is the output of the quantizer, okay, in the middle, and then the x hat will be somewhere in the middle here, right, which is the reconstruction. So let's take this very simple example, okay? I will have bounded input x between negative 16 and 16. So this is negative 16 and this is 16. Okay? I will throw away the two least significant bits. I will throw away the two least significant bits. Okay? So, how do I work out this problem? I will throw away the two least significant bits. So I have this. Okay, the decimal points is right here. So I throw away all the fractional parts. I also throw away the two least significant bits. Okay, but I keep the rest. And this is y with a sign bit right here. Okay, now let's think about this. Okay.